So now let's take a look at a few examples. And the first one is a basic K-factor problem, kind of similar to what we did before, where we have a simple circuit. I'm regulating at 1.05 per unit at the top of the feeders. And I've got 3 loads in the circuit and 3 line segments. And so one thing that's a little bit different in this case is I want to start tracking losses. So I want to see what kind of difference the capacitor placement at location 2 is going to have on the losses. And so what we're trying to look at for voltage is what's going to happen with this voltage at 3. So keep in mind that the section load that I'm going to use for the voltage drop calculation is just simply based on what's the load in the section plus what's the load below that. And you can see that the net load on that top section is going to be 3,000 plus 2,000 plus 2,000, which is 7,000 kVA. So when I do a loss calculation, what I need to get is I need the current magnitude. And the current magnitude is going to be the apparent power divided by square root of 3 times line voltage. The apparent power is going to be the square root of P squared plus Q squared. And so P is going to be 7,000 times the power factor. Take that square, add that to Q, which is 7,000 times sometimes what we call the reactive power factor, which is the sine of the power factor angle. So take the square of Q, add these 2 components up, take the square root, that gives us S. Divide by square root of 3 times voltage. And since I just need an estimate, and if we look at this as being sort of like the first iteration of a power flow, I'm just simply going to use nominal voltage there. And so this is going to give me a guess for the current of 324 amps, which I can then use to calculate the loss. So this current squared times 3, because this is 3-phase, times 3, so I have 3 miles times the resistance per unit length is going to give me the loss in that first segment. The other 2 line segments have less current, and so they both simply have 2,000 kVA each at power factor 0.85. And what we're doing in this case is just simply doing the same calculation. We get the current, and then based on the current, we can calculate the loss, and we get a net loss in this case at this loading condition of 336 kilowatts. So again, you can think about this as being the calculations you would make in the first iteration of the power flow using nominal voltage as a starting point. So the next thing we could do is we can calculate the voltage drop, and we're going to calculate the voltage drop using K factors. And so I'm going to have S times the K factor times 3-phase power. Now, if you wanted to get these values in terms of per unit directly, normally they're in terms of percent. Instead of using 10 to the 5th, you can actually use 10 to the 3rd and calculating the K factor. And that'll give you the K factor in terms of per unit voltage drop per kVA line miles. And so here we got the K factor where we're taking the resistance times the power factor. We got the reactance times the reactive power factor. This is all divided by the line to neutral voltage nominal value squared. And if we plug in for the load, we get a drop of 0.081 per unit, which is quite substantial. Do a similar calculation for segment 1-3, and then we're going to get a voltage drop of 0.0231. So at the end of the circuit at 3, take the top of feeder, subtract off the 2 drops, and then we get a voltage of 0.9461 per unit. Next, what we do is we look at the impact of adding the capacitor at the end. We say this is going to be a 1200 kVAR capacitor. And so in this case, if we're looking at the change in current, what happens is that this capacitor is its Q is going to cancel out with the Q that was originally flowing through the line segment due to the load. And so any segment that's between this capacitor and the substation gets impacted, like the it's injecting that 1200 K bar and it's going all the way back kind of toward the source. So it has no impact on section 1.3, it just has impacts on section 0.1 and 1.2. So what I can do in this case is I can then subtract off this 1200 K bar from the reactive power for those two segments. And what this will give me a current of 298.6 for the first segment and 79 amps for the second segment. The third segment's going to be not changed, it's still going to be 92.6. So by lowering current on the first segment and the current on the second segment, that we've reduced the net losses. And so again, you can think about this as being the first iteration of the power flow. So you definitely see in this case what's going to be the impact on losses. To see the impact on voltage, then what we're going to do is we're going to calculate the boost effect. And what we have in this case, as far as the change in the voltage drop, would be we're going to get a change in voltage drop across this first segment from 0 to 1, where this is going to be the K factor for the capacitor pre-multiplied by S and post-multiplied by the capacitive K bar. And so in this case, you just substitute in for theta equal to minus 90 degrees. This gives us minus 0.642 times 1,000 divided by 7,200 squared times 3. You multiply by the line length, you multiply by the size of the capacitor bank, and this is going to give us a change due to the capacitor, adding the capacitor, of minus 0.0149 per unit. And all we need to do is we just basically need to add this change in drop from 0 to 1 of this minus 0.0149, and then we get the impact here at 3. So note what I'm doing here, when I'm doing this sort of calculations, I'm using this principle of superposition. We're doing linear circuit calculations here. So what you can do is you can look at the change in voltage drop due to the load, and you could superimpose on here the change in the voltage drop due to the capacitor. Now, one thing that people get tripped up on is when you're looking at what difference is the capacitor going to make in terms of voltage drop on what bus. Some people have some difficulty with that concept. And so basically, if you go back to this original circuit, and let me go ahead and erase this a little bit. Okay. Now, what's going to happen is that when I put this capacitor in here, it's basically going to change the VAR flow from 0 to 1, right? It's going to cause a change in voltage drop here. There's going to be a change in voltage drop from 1 to 2 due to the capacitor bank. There's also going to be a change in the voltage drop across here due to the capacitor bank. And so what's going to happen in this case is that bus number 2 is going to have the voltage change by the sum of both these terms. But what about bus number 3? Well, bus number 3 just sees the impact of the change at bus number 1. And so I only add to bus number 3 this particular term right here, because the common line segment between bus 3 and where I've got this capacitor is only this section right here. So what you have to be kind of careful about is you got to kind of know what bus you're looking at the impact at, because again, we'll have a larger change at bus number 2 than we will at 3, because for bus number 2, you got this additional change, but for bus number 3, you're just looking at the change in bus number 1, right? So anyway, just kind of watch out for that. This is a little bit more sophisticated case where we're looking at a system and I want to do a fixed capacitor bank size. I start off with doing a base case calculation. And what I want to do now is I want to figure out, well, how much capacitance do I need to add in K-bar at bus 3 in order to keep the voltage at bus 4 from dropping below 1 per unit. And so I'm going to round this off to the next 300 K-bar. And then I want to kind of verify that I've been able to maintain the voltage at bus 4 to my correct value, and I want to know what the new value of losses is going to be. And so here's the circuit in this case. This is the load I'm concerned about for the voltage, but I'm actually adding the capacitor to bus number 3. And what we'll see later on when we go through and we do the second part of the lecture on capacitor applications, you don't always want to put the capacitors at the end of the circuit. As far as loss reduction, there's actually some rules of thumb where basically that might be better more at the midpoint or maybe 2/3 the way down the circuit. So you don't just simply put your capacitors at the end because that gives you the maximum voltage boost. That is not the solution if you also want to minimize losses. So here's a circuit we're working with. We've got 1.04 at the top of the feeder. So this is very similar to what we did before. In this case, I'm doing these terms in terms of percent voltage drop this time. So this is, I'm using 10 to the 5th here. I'll calculate the K factor and I get the K factor in terms of percent voltage drop per kVA mile. And what I start off by doing is I just simply start calculating the voltage drop across each of these different segments here. So I have voltage drop from 0 to 1. It's 1.5 miles times the K factor times the net load. And the net load is just a summation of all the load, either on the segment or below that point. So this is going to be 3.45%. Do a similar calculation for the voltage drop from 1 to 2. Again, I've got less load on here, so I'm going to have less voltage drop. I'm doing voltage drop from 2 to 3 and also from 3 to 4. And if you want to find the net effect, then basically you can just simply add all that up. And then what we're going to see at bus number 4 is going to see 1.04 minus 7.785%. You can divide by 100 to get that in per unit. And what we see at the end of the feeder is 0.962 per unit. So we're a little bit on the low side there. You can do the line current calculations as well. I'm not going to spend as much time on that because we did this before. But basically, you're just simply taking P squared plus Q squared in each segment, and you're converting that to current. Or if you do have some of these currents calculated, you can just add it up to what you have on the segment below. And you could use all this information to calculate the net losses, and this turned out to be about 206 kilowatts. Now, what I want to do is I want to get a boost so I get that voltage at the end of the circuit up to 1 per unit, right? And when I put the capacitor into the circuit, what I'm going to have is I'm going to have a K factor, which is going to be X times the sine of theta divided by voltage squared times 10 to the 5th over 3. Substituting for theta equal to minus 9 degrees. And what this does, this gives me the K factor for the capacitor. And I'm going to apply superposition in this effect, in this calculation, to see what kind of capacitance I need to get the desired boost target. So if I want to have like 1 per unit at the load, and the voltage drop on that last segment is 1.066%, then basically the amount of voltage boost, the amount of voltage that I'm going to need at bus 3 is going to have to be 1.01061 per unit. All right. So if this is what the voltage drop is from 3 to 4, and I want bus 4 to be at 1 per unit, I got to really figure out how to get bus 3 to this particular value. So using the K factor for the capacitor now, the voltage at bus 3, we can determine that to be 0.973 per unit. And the change of voltage I'm going to need due to the capacitor is going to be this original voltage minus my voltage target, which is this value in per unit. So basically, this is like I need a negative drop in a way. In other words, I need a boost. And what I can do is I could set this equation up where instead of solving for the voltage drop, I just simply solve for Q. I work backwards. And so if I have a voltage drop target, what I can do is I can divide through by my line length times K, and that's going to give me Q for the capacitor. And so in this case, the line length from the capacitor all the way up to the substation is going to be 4 miles. And what I figure in this case is I need 2320 kbar in order to get that type of a voltage boost. Now, we know that capacitors are typically in fixed size increments. And so what I would need to do is I would need to round that off to the next higher kbar because I want to make sure I hit my targets. And so if 300 is the increment, I go from 2320 up to the next integer size combination, which is 2400 kbar. And then if I plug back into the voltage boost calculation, I see I'm actually getting minus 3.89% drop change. And then what you can do in here is you can go through and you can recalculate the voltage at bus 4. Basically, what you can do in this case is you can add to that the amount of change that you're going to get due to the capacitor addition. And what you see is you do get this pretty close to 1 per unit. And so anyway, what you can do with the K factor is if you know what you need for the voltage change, then you could use that capacitive K factor in order to figure out what amount of Q you can add in there. And then you use that as like for these types of planning calculations. The other part of this problem here is we're going through and we're updating the line current and we're updating the losses. And this is a little bit trickier set of calculations here. I'm not going to spend a lot of time on this, but basically what you're doing is for the line segments that are seeing this capacitor bank, what you're doing is you're basically calculating the new Q flows. And with the new Q flows, and you're going to get different sets of current values on the lines. And then this is going to give you an updated value for the losses. And you see indeed that the losses go from 206 down to 172.8. All right, so kind of a complicated set of loss calculations. This is, why we do power flow programs, but you could actually figure out, what sort of capacitance you would need to have in there in order to get the desired amount of voltage boost. All right, this third problem's kind of a combination of two, in that we're still looking at trying to hit a minimum voltage, but the thing that's a little bit different in this case is we want to make sure we don't go over maximum. And this particular circuit, it's shown right here, kind of similar to what we had before. What we're trying to do is we're trying to keep all these voltages within a certain range. But the problem is that these loads that I'm showing, these are peak values. And the problem is that when I put a certain amount of capacitance in there, that's good for the peak condition. And if it turns out that I'm in a light loading condition, if I have fixed capacitor banks, well, that's going to cause the voltage to shoot up above my maximum limit, right? And so this is where I'm looking at, well, if I have capacitance out there, how much of that would be fixed and how much of that would be switched? So you have some design constraints in here that you can add these capacitors in increments of 600 kvar. You want to keep all your voltages between 1.034 and 1.017 per unit. And basically what I'm trying to figure out is if I'm under heavy load conditions, how much capacitance would I have to have? If under light load conditions, which is 50% of my peak, then how much capacitance would I need to take out? In other words, how much of that capacitance would have to be switched? So you go through a very similar calculation that we did before, where you're working with the K factor and you've got these voltage drops. Note in this case that we have distributed load on this last segment. And so what we're having to do in this case is we're having to use a factor of 2 in here. And you could either use a factor of 2 on the length or a factor of 2 on the load. It doesn't really make any difference. You're calculating the voltage drops across the segments with no capacitance in the circuit. And what you're seeing is for your voltages at all these different buses, that the voltages are just too low. And the worst case voltage is typically going to be at the end of the circuit, right? Next thing you do is you would start to think about, well, how much boost do I need to have, right? Basically, if the end of the circuit is probably going to be my worst case value, I want to go ahead and do my design so I have 1.017 at bus 3. Then if I add to that the voltage drop from 2 to 3, that means I got to get bus 2 up to 1.023. And so the amount of boost that I need is going to be my original voltage minus my new target minus 0.054. And again, I calculate the K factor for the capacitor. And then given I need a certain amount of voltage boost, I would plug in for the line length and plug in for the K factor for the capacitor. And this gives me the amount of kVAR that I need to have. And again, given that this has to be increments of 600 kVAR, then you go up to the next larger size, which would give you 7,800 kVAR. So anyway, what you're going to end up with is, as far as the new the changes in voltage, you're going to get a change in voltage from 0 to 1 and from 0 to yeah, you're going to get these appropriate changes in voltage right here. Yeah, so you got the length times the K factor for the capacitor times the 7,800, and then basically what you can do is you could use this to update what you're going to have for the voltage drops. And so basically what you're doing in this case, you're just adding up what you're going to see as far as the impact of the capacitor. Again, you can apply superposition in this case. So if this is basically the impact of the load, what you can do in this case is you can superimpose the impact of the capacitors. You can see from these values that we're still below our maximum. We're above our minimum, but we're also below our maximum. We set our maximum in this case was 1.034. Okay, now what happens if we're at light loading conditions? Well, light loading conditions, now what happens is all our loads get halved. And so what this means is all original voltage drops got halved. And so now, if you look at these voltage drops due to the load, and you would add to that the changes in voltage that are due to the capacitors, what you're now going to see in this case is we're too high, that we've actually got voltages that are 1.058, 1.061, 1.044. The voltages just basically go above our maximum condition. So now what we have to do is we have to figure out, well, how much capacitance do we need to take out in order to get these voltages back down? And so anyway, in this case, what we end up with is if we have, like say bus 2, which we'll work at capping to 1.034, we look at this difference in voltage, we have this change in voltage which we need to achieve in per unit, And what we're basically doing in this case now is we're trying to figure out, well, what would be that capacitive target in order to get us back into the right limit again, right? And so anyway, this is probably on the kind of the complicated side of it, doing these examples with K factors right here. But basically what you find out with this is how much of this needs to be fixed and how much of this needs to be switched. So anyway, what you end up with is you just need a fixed value of 3,600 and you have a switched value of 4,200. So later on, when we do this stuff in part 2, we'll be using the computer program for this. This is kind of getting to the edge of the sort of analysis we would want to actually be doing by hand here, because there's a lot of bookkeeping you're having to do in this case. But this is actually what you would actually have to be doing when you're putting capacitors out in the field, is you don't put out one big capacitor. If you put out one big capacitor, it's great for peak, but it's not really good for all sorts of different loading conditions. And so typically what you would do is you might start out at, say, like 10% loading, and you see how much capacitance you need and go up to 20 and 30 and 40 and 50%, et cetera. And then what you would do is you, by kind of trial and error, would kind of figure out what would be kind of the best mix of sizes and locations associated with that in order to get kind of like a good solution. Okay, so anyway, this is just kind of an example of how you could actually use this for doing some of the fixed versus switch sizing. So just for some references on this, if you want to know more about the basics of doing this control, the Tom Short book's kind of a good reference for this. They get into capacitor ratings and the same sort of stuff I talked about here. Probably get more in the nuts and bolts than what I did in this particular lecture. And what I just kind of talked about in this case, which is kind of limiting, was I was assuming that you had a fixed location, which makes this kind of awkward because this may not be the best location. You're given this location to work with, and all you can actually do is size it. But in the reality, you have 2 dimensions to this problem, actually 3. One would be where to put this, okay, where to put capacitors. The other one would be what locations, what multiple locations, so you use 1 capacitor, 2 capacitors, 3 capacitors, and then what would be the sizes. And we'll be getting into that in kind of the next lecture of, in general, where do you put the capacitors, what sizes, and what's kind of what you would look at the circuit, you base your decisions on.